this video, we're going to talk about the symmetry of a molecule, how that can influence whether or not a molecule is chiral, and then what are meso compounds. Okay, so first off, it's important to point out that if a compound only has one chirality center, it's going to be a chiral compound. And so most of this video really applies to molecules that have more than one chirality center. It's good to keep in the back of our mind, and don't forget that if there's only one chirality center, the molecule is going to be chiral. That being said, if there's more than one chirality center, a compound may not be chiral. If it has a plane of symmetry, then it's not going to be chiral, and it's going to be identical to its mirror image. Now, there are a lot of different types of symmetry. The one that we're going to focus on in this video is when molecules have a plane of symmetry. So let's look at some examples of that on the next slide. Okay, in this first example, we're looking at the two isomers of 1,2-dimethylcyclohexane. And we have the trans isomer, where the methyls are going up and down, and then we have the cis isomer, where both methyls are pointed in the same direction. In this case, the cis isomer, and I should say both of these isomers have two chirality centers, right? Both this carbon and this carbon in both of the molecules are chirality centers, right? Now, it turns out that the trans isomer is chiral, while the cis isomer is not, even though they both have two chirality centers, right? And the reason the cis isomer is not is because it has a plane of symmetry, right? If I put this plane here through the center of the molecule, it's identical on both sides, right? Or I could get one half of the molecule by reflecting through the plane to get the other half. Whenever we have these planes of symmetry, it means that that molecule, even though it has chirality centers, is not going to be chiral. It will be achiral. All right, so it's important to be able to spot these planes of symmetry. So we have a couple different examples here. We want to decide, do they have planes of symmetry? And so I think this cup and saucer does have a plane of symmetry. The plane of symmetry that includes the handle, right? If the plane of symmetry bisects that handle, then the cup will be identical on both sides. Right? In the case of our hand, I don't think we have any planes of symmetry, right? If I try to put a plane of symmetry here, right? I've got the thumb on one side, not the other, right? I might sort of cut the hand in half, like, if this blue thing was the plane of symmetry, right? But if you look at your hands, right, the back of your hand is not identical to the front of your hand, so our hands have a plane of symmetry. Right, this chair, I think if I put the plane right down the middle of the chair, it would have a plane of symmetry, right? But then on this chair, when I put this desk on the side, right, it's no longer identical on the left-hand side and the right-hand side, and I can't see any other planes of symmetry in that chair. All right, so let's do the same thing for a couple molecules. Right, so I want to know whether each of these molecules has a plane of symmetry or not. And so I think in this first case, right, we do have a plane of symmetry. Right, if I put it right down here, right, the top side is identical to the bottom side. Right, if I look at this molecule, I might first consider, right, what if the ring is a plane of symmetry, but in this case the chlorine is not identical to the bromine, so that's not going to work. But I can put a plane of symmetry, essentially like this, where I bisect, right, where that plane, cuts through the center of, right, these atoms and these atoms, right? I bisect the chlorine and the bromine, right? Then the back side is going to be identical to the front side, and so that would have a plane of symmetry. When I look at this example, I say, oh, I could do the same thing, right? But in that case, it's not going to work because I would only have one carbon in the back, two carbons in the front, and so this molecule does not have a plane of symmetry. Right? In this case, I think it does, right? If I put the plane right here, it's identical on the left-hand side and the right-hand side, and so that molecule does have a plane of symmetry. Okay, so the name that we give to these molecules that have multiple chirality centers, but because they have this plane of symmetry, they are not, in fact, chiral overall, we call these compounds meso compounds. And so the way to recognize a meso compound is, first, to be meso, it's got to have chirality centers, right? If it doesn't have chirality centers, then I know it's just not chiral. So a meso compound has multiple chirality centers, but then it does have a plane of symmetry, meaning that the molecule overall is not chiral. It will in fact be identical to its mirror image. Another way to determine if we have a meso compound is we can look for plane of symmetry, but also if we draw the mirror image of the whole molecule, and if it's identical or superimposable on the molecule that we started with, then we also know, right, it must not be chiral, and so if it had chirality centers, then it would be meso. So this is an issue that we're going to deal with a lot less. We won't really see any examples of this, but I just wanted to make you aware of it, particularly because the book does as well. So we've seen that if a compound has multiple chirality centers and it has a plane of symmetry, it's going to be achiral. But there are other types of symmetry. Another type of symmetry is inversion symmetry. And so if there's a point in the molecule where, if I flip all of the atoms around that point, if I get the same molecule, it has a center of inversion. And so this is an example of a molecule that does have a center of inversion. And this molecule has two chirality centers, right? And it doesn't have any planes of symmetry, but because it has this center of inversion, it is also going to be achiral. So, like I said, you're not going to see any examples of this, but I think it's good to point out just, there are often more complicated examples even, than we get a chance to see in this course. All right, so to kind of sum things up, when a compound has multiple chirality centers, but it has a plane of symmetry, that compound is meso and it's going to be achiral. But when a compound has multiple chirality centers and it does not have a plane of symmetry, it will generally be chiral, right? Of course, we just saw there are exceptions, such as if it has a center of inversion. All right, so this slide may be a little bit redundant, but we can go ahead and go through it. Right, a compound with chirality centers, but it's achiral because it has symmetry, is called a meso compound. And so all of these are examples of meso compounds, right? This one has two chirality centers, but has a plane of symmetry here, so it would be meso. Again, two chirality centers, but a plane of symmetry here, so it would be meso, right? Again, two chirality centers, but we have a plane of symmetry here. All right, so just a couple examples. We want to know if the following compounds are chiral or achiral. And so when I look at this first one, it only has one chirality center. So I don't have to look for planes of symmetry or anything. If it only has one chirality center, then it's going to be chiral, right? This plane of symmetry only applies when we have multiple chirality centers. So that will be chiral. In the case of this second molecule, right, I have a plane of symmetry there. Even though it has two chirality centers, right, it is going to be achiral, right? It is meso, right? And then in this example, in the bottom, right now, because I've got one methyl going up and one methyl going down, right, there isn't a plane of symmetry here. There's not a plane of symmetry in the ring of the molecule, and so this compound has two chirality centers. There's no plane of symmetry, so it would be chiral. All right, so one last example. There are a number of examples that you'll see in the book where it's helpful to think about and remember the fact that we can rotate about single bonds. And so when we see this molecule and we want to know whether it's chiral or achiral, right, I say, well, I have two chirality centers, and at least at first glance, in the way they've drawn this molecule, it doesn't look like there is a plane of symmetry, but we are free to rotate around this bond. And so I could redraw this molecule, right? And so if I rotate it so that the two methyl groups that are in the plane are now pointing to the same side, right? Then that, when I rotated that around, right, our original bromine, we didn't move, right? This other bromine, when I rotate this guy, is going to be pointing up as well. And so this molecule does, in fact, have a plane of symmetry. And so it's going to be achiral. So you just want to be careful. Sometimes if we rotate around the single bonds, we may be able to draw the molecule in a way that allows us to see its plane of symmetry.